Yeah, I'll put it in my. How does this work? So is this okay? This doesn't go up and down. Okay, it works this way. That's good. All right. Welcome everyone to my talk about improved post-processing of heat transfer experiments using the finite element method. This is work that I've done with my supervisor, Nick Atkins, during my PhD. And Joe Dean was a crucial element in getting the finite elements into this work. And that's what I'm going to present to you today. So transient heat transfer experiments are usually conducted when we're interested in convection-dominated problems. At the bottom of this slide, I've put the Newton's law of cooling. And the property of engineering relevance that we want to find is the heat transfer coefficient, abbreviated as HTC in the rest of this talk, indicated in red. And I've given here an overview of the rig that I've used in my PhD. And there's a lot of things indicated on here, but I just want you to focus on the heater meshes and the test section, where an IR camera is focused at the test section with an object of interest. And I just want to get you the general idea. It's like a wind tunnel experiment where an airflow is going through this rig. So if we zoom into the test section, for instance, on a backward-facing step in this example, what we measure is the free stream temperature, using a turbocouple usually, and the temperature of the surface we're interested in, which is the temperature of the wall. And we conduct these experiments by first introducing a near step change in free stream temperature. And as you can see, using heater meshes, we can get pretty close to a perfect step. It's not exactly that, but it's something. And what we then do is we measure the thermal response of the test plate to that step. So we see how this the plate heats up in response to the step change in free stream temperature. And we collect the temperature data in time on every pixel on the plate that the camera can see. So for a well-conditioned experiment, we need to do a couple of things. First of all, we need to make sure that we can have enough measurement points. So we need a camera with a high frequency of measurement, usually around 200 Hertz. What we also need is this thermal response to be sufficiently slowly. You don't want this blue line to shoot up like the red one, because then we can't measure anything. We just see like instant heat, and it's very, very hard to come up with the HTC. Because you need to remember, the only thing we measure are temperatures. Getting the heat transfer coefficient is all done in the post-processing. So this is really important that we get a material with a high thermal effusivity, so we can slow down this thermal response, as you can see here. And finally, previous work by Playford has indicated that the biggest factor in reducing uncertainty in this experiment is having a high free stream temperature step. And this is really important because this essentially means that heat transfer experiments are usually small scale. Because to give you numbers, if you want a 30 Kelvin temperature step for a mass flow of 1 kilogram a second, that's already 30 kilowatts. That is quite small domain, 1 kilogram a second. So yeah, it's important that we can conduct these experiments small scale. So I've told you that we measure the temperature, but how do we get to the HTC? So if you look at Newton's law of cooling and you assume, which is usually a good assumption, the experiments we're interested in, that the HTC and the free stream temperature, adiabatic wall temperature, is constant, you can solve the system of equations by assuming you know the temperature and the heat flux at two different points in time. And you know then that HTC will be given by the equation I've put on the slides. But it will be much more clear to you if I just show you what happens if we calculate the corresponding heat flux to every temperature point we have in time. You will see you get like a clear line. You can fit by regression, like a line through this data, and the negative of this slope will be the HTC. You can see in the beginning here that this point is not very useful to us, and that is due to the fact that we cannot achieve a perfect step change in temperature. So this data we cannot use. Part of the post-processing is deciding which data is useful and which one is not. So really, what we need to do, what the key part is in these kind of experiments, is how do we get the heat flux? We can't measure it. So how do we get it? So, oh yeah, just to show you, if you use this post-processing for every point the camera can see, you get these really nice contraplots of HTCs. This is downstream of a backward-facing step, with a step over here, recirculation zone over there, And then here, the reattachment point with increased heat transfer coefficient. So what's currently used to post-process these experiments is a very simple method that assumes 1D conduction as semi-infinite domain. So you have a convective boundary condition on top, and you assume that your substrate is so thick that the temperature on the backside of it will always remain at the initial temperature. And for these kind of conditions, the heat flux is an analytical solution. And some clever people have found all sorts of ways to post-process that. And the most famous one, which is used in abundance in the literature, is the Oldfield method. It's just an impulse response reconstruction of the heat flux. My supervisors once called it the most beautiful 2 lines of MATLAB code he has ever seen. And why it is really simple to implement. It's quick. And even though it looks like a gross oversimplification, it's surprisingly accurate. However, there are regions where this kind of methods will fail, and it does put constraints on your experiment. So the longer you do your experiment, the heat will inevitably transfer through the material. And as soon as the heat pulse reaches the backside, you breach the semi-infinite conduction, the semi-infinite assumption, which will get an error in your result. So this is the formula we use to estimate how far a heat pulse penetrates in the material. So effectively, just scaling up your experiment's not a solution, because then you would run into the trouble of needing an excessive heater measured with like megawatts of power supply. We don't want that. So instead, we need to use a material with a very low thermal diffusivity. That's important. And it's not just important because the heat pulse travels into the material, also close to boundaries where we can't measure things. In this case, the step wall, the lateral error will be as much as the penetration depth. So it's in our best interests to find materials with both a high effusivity and a low diffusivity. And usually thermoplasts like polycarbonate are quite good for that. There are other examples where the semi-infinite method fails. For instance, if we have a step change in boundary conditions, it's quite an extreme case, I know, but you get some fluid cases that can approximate that. We get lateral conduction with an error just as large as the penetration depth. So the longer you run your experiment, the more you get like smearing out of your results, close to a step change. Maybe more applicable to aerospace engineering is a turbine blade, as I've shown here. You can see at the leading edge, because of the high curvature, the 1D assumption will fail completely. And in the trailing edge, we have a different problem. It's getting quite thin over here. So you see from these penetration depth schematics, the semi-infinite assumption will fail there. So can we do this better? And this gave us the idea to try to post-process these heat transfer measurements using Phoenix. So we use a mixed methods to solve the heat equation in a FE model of the object under study, and we use the temperature data that we get from the experiment as a boundary condition. So first of all, I'm going to show you that if we try this FE methods using data from an experiment designed to use with the 1D semi-infinite assumption, we get quite a good match. And then second, I'm going to do a couple of virtual experiments, which I will explain later, to show what improvements we can get. So I'm definitely not claiming that no one else has tried to do FE post-processing, but it's usually with like black box, like expensive software packages. With Phoenix, it is open source, fast, and highly customizable, which is a massive advantage for use in academia and industry alike. So if we get back to the experiment of the backward-facing step, what we have done is we have just made an FE model from the bit of the polycarbonate test plate that the camera can see. On the top, we put the experimental temperature data as a Dirichlet boundary condition, which is also a function of time. And here on the bottom, we just say temperature is equal to the initial temperature of the experiment. And we just put like adiabatic side boundary conditions, which is usually pretty good approximation. So if we then look at the match here, you can see that for both the backward and the forward-facing step, we get a really good agreement, bar in a little layer which is affected by lateral conduction errors that I've shown you before. That's a good result. If we then design a virtual experiment where we apply the heat transfer coefficient and the temperature as we would want to measure, first in a Phoenix simulation with a Robin boundary condition. The response, the temperature data we get in response to that on that boundary is our experimental data. We put it in another simulation where we put that data as a boundary condition and we calculate the heat flux. And then we do the same, we calculate the heat flux again with the 1D semi-infinite methods, calculate the HTC with both, compare the results. Simple as that. So a first case is a very abrupt change in free stream heat transfer coefficient. You can have this kind of thing in, for instance, a boundary layer transition from laminar to turbulent. Not as extreme, of course, but it's an approximation. And as you can see, the semi-infinite 1D assumption methods fails completely. Over more than a penetration depth, the results are really quite poor. Whereas in Phoenix, you just get like a little deviation at the intersection, which is probably caused by a little bit of a two-course mesh in that area. Then, the second case is an aerofoil, which is based on the Harrison cascade, which is very popular in the literature. And I've sketched like an HTC distribution to give you an idea of what we should measure. At the leading edge, high heat transfer because of the stagnation points. We get boundary layer transition on the suction surface, which is the top side of the blades. And we get like a growing boundary layer, which remains laminar on the pressure surface. So how do the two methods do on this one? So we compare the results for the suction side and the pressure side. We see that we have a good match on the suction side, and on the pressure side, we see the expected result that the 2D performs better at the stagnation point, as I've highlighted earlier in the talk, and at the trailing edge region. So to wrap up, I've presented that the FE-assisted post-processing matches the 1D results, 1D post-processing when we expect it, and we can get improvements for both a step change in free stream heat transfer coefficient and the distribution around an aerofoil. What we now want to do next to further improve accuracy in post-processing is use temperature-dependent material properties in our FE model. So thank you very much for your attention. I'll take now any questions.